again, and I have already posted some information on that, some practicing materials in 2 flavors, no less. First, an online quiz, practice quiz, okay, non-graded, just for you to play with. You can go in there, do the questions. These are kind of representative questions. They came from exams from previous years, okay? And you can just play around with that. And I also put a kind of in-class style practice quiz, okay? I have more practice quizzes, so if I'm in a good mood, I may post even more, depending on how nice you guys are to me, okay? And I can be nice in return. Very simple. I have lots of practicing materials, so I can post more if you guys are not get overwhelmed. Any questions about that? The quiz will pretty much be done in the same fashion, so it's going to be in class, same rules, same amount of fun as we had last time. Okay, so something to look forward to. Yes?
You're still allowed to bring a note card, right?
Yes. Yep. One note card. Both sides can be used, including the sides. Can be used. If you write very tiny, you can use more information there. So, yes.
Will it just be the content after?
Yes, it will not be cumulative. It will basically be whatever we talked about after the first quiz. The new stuff is what we're going to kind of like try to cover on the quiz. Then the final, of course, is cumulative. It's the whole thing. Okay, so we're making progress with this course quite a bit. We have done some good work so far. We have talked about the hydrogen atom in the context of quantum mechanics. We found solutions for that problem. Then we moved onward to more complicated atoms, helium, lithium, and so forth. We had to make some approximations, but still we get pretty good descriptors of what the states are, if there's more than one electron. Spin is important, as we learned. We know something about the size of an atom. We know something about its ionization energy. So we actually kind of painting the picture that we set out to do at the beginning of this course. We're getting there, okay? But as a chemist, you may still feel a little unsettled because we have talked only about single atoms. And as we all know, that's not really chemistry. Chemistry involves more atoms. We want to make some molecules, and we have to move on towards the molecular value. And so quantum mechanics will again be our guide here. And evidently, because the problem gets more and more complex, we will have to make, again, some approximations. But those approximations are sensible, and they will follow similar rules, so to speak, that we have already applied, okay? So here's the first kind of consideration that we should focus on. Here is a carbon atom, and I'm going to focus on the valence electrons of this carbon atom. What are the valence electrons? Those are the electrons in the open shell. Okay, hopefully you know that. Because, of course, the n equals 1 shell is full. That's called the core shell, and basically that means if it's full, that shell doesn't really participate in the chemistry of this thing, and so I can kind of forget about it. What I should focus on, if I would like to understand the chemistry of this atom, I need to focus on the open shell. Those are the electrons in the open shell called valence electrons. That concerns the 2s and then 2 electrons in the 2p, 4 valence electrons plus the 2 electrons in the core, which I don't consider here, is a total of 6 because that's the atomic number of carbon. Okay, so according to this diagram, we have 2 electrons in the 2s, and remember these 2s electrons are valence electrons, okay? And I have 2 unpaired electrons in the 2p. Okay, so if I now sketch that, that's given in the picture up there, then I see these lobes, and that's the p, those are the p orbitals. The 2s is kind of like a spherical thing. Okay, so think about there's a sphere there, there's 2 electrons there, which I don't depict in this image. I only show where are those 2p electrons. Okay? The p orbitals are these lobes that kind of are aligned along the axis. So basically, it's this orthogonal alignment of this kind of like dumbbell shape. One here, one there, and the other one orthogonal to it, right? So that's the picture. X, Y, and Z are arbitrary axes in a way, because I can rotate it, and it will still be the same. But for my purposes, I just choose a frame and then lock them in that frame. So if I put those two electrons in there, and let's put it in px and py, why not? Could also be in pz, doesn't matter. Just have to put them somewhere, so py and px, and there they are, unpaired electrons. Now I would like to do something with this atom. I would like to bind it to something else, okay? For instance, I'd like to make a very simple molecule, methane, CH4. That means I have to put 4 hydrogen atoms onto this single carbon atom. That's it, CH4. And I'm going to ask myself, where am I going to put those hydrogens? Well, I can say, well, there's 2 unpaired electrons here in this atomic carbon. Those 2 electrons could pair up with a single electron that each hydrogen atom has. And if they pair up, they will form a bonding pair, okay? And therefore, that seems to be a very plausible way to proceed. So, naively, that's what I'm going to do. I'm going to put a hydrogen atom there. I'm going to say that single electron from hydrogen, let's say if I assume that it is the opposite spin, then they can kind of like some way, somehow come together and pair up, and maybe that will form a bond. Okay, I'll leave everything open right now. I don't know what I'm doing yet, and we'll paint the picture carefully, but that's the general idea. Okay, so there's one. Second one goes, well, it goes along the x, okay, something like that. And so I have 2 hydrogens accounted for. Looks kind of all right, but I'm also realizing this is maybe not exactly what I want to see, okay? Because the 2 electrons in the 2s, which is this spherical thing, they don't point in a certain direction. So what am I going to do with those? I don't really know. And they are paired, I mean, they're not unpaired, so do they pair up with hydrogen atoms as well? And how? What is the configuration for that? And then also I realize, I mean, the angle here is like 90 degrees. I don't like that angle at all, because I know from other classes that it should be 109.5. All right, so what's going on? Is quantum mechanics completely failing me here? Okay, what's going on? I want this. I mean, this is not true, so I want that. I want this like tetrahedral shape where all angles are 109.5. You see something that's called sp3, that's what we want. But why do we have that, and how do we get that? And what is the justification for that? Actually, does anybody know? I mean, you guys have used this probably for several years. Why is this a thing at all? What does it even mean to have this configuration compared to the atomic configuration up there? Why is this valid in the first place? Yes?
But it has like a more stable configuration, so everything is more comfortable and not overlapping with each other's energy.
Yeah, I mean, yeah, something along those lines, right? But how does it relate to the quantum mechanical picture up there? What is the relation between those? I mean, how do we get from that to this? Why is it not this and it actually should be like that? There must be a physical reason for it. And it's somewhat along what you just said. Okay? So, I mean, I'm going to rephrase what you said. Okay? I'm going to rephrase, but now in quantum mechanics speak. Remember, that thing up there, the atomic picture, which is a single atom by itself, all by itself, the orbitals followed from me solving with you guys, not just me. This is a joint experience, remember? Solving the Hamiltonian, okay? Solving the Hamiltonian, which is basically the Schrödinger equation, finding those orbitals and then say, this is it. But that was true only for a single atom all by itself with nothing else around. Okay? If that atom is now surrounded by different things meaning other atoms have nuclei with charges, plus charges, and their own electrons, negative charges. I'm going to bring that into my system, I'm going to bring it around my atom. Those charges will start interacting like crazy, repelling, attracting with the charges of my single carbon atom. So, in other words, this individual atom all by itself is just fine, but it is not this, because this atom is not by itself, and is surrounded by a whole bunch of things, charges that pull and push. Therefore, change the whole situation. They change. This situation here is not the same as that at all. So what do I have to do? In order to get from there to there, I have to look at my Hamiltonian and include all those interactions. Okay? I have to include all those interactions of these hydrogen charges here that interact with the charges that the carbon atom brings to the picture. I can tell you that solving that problem is going to be a tremendous pain in your derriere. Okay? You don't want to do that. Solving that completely is virtually impossible. Computers can help you out. That will be an approximation still. But we don't want to get into those nitty-gritty details. We'd like to have a better description which is simpler and basically hits the problem on the head in a more intuitive way. Okay? A simpler description that does basically the same as opposed to solving this entire new problem with all those charges interacting with one another. Extremely complicated. So what am I going to do? This is very important. I'd like you to understand this. You'll probably forget about it immediately after you pass this class. You're like, eh. But in the beginning of this course, I made a big stink out of, you can have, if you have a complete set, remember this, complete set of eigenstates or eigenfunctions, out of the complete set, I can make any function I want through a linear combination. Remember that? Several lectures I was emphasizing this. And you wondered, like, why? Why is that so important? Well, it's important here because I'm going to use that exact concept to simplify my description. What I'm going to do is, I like those orbitals because they're kind of like quasi-exact, okay? At least for hydrogen they are. They're completely analytical, perfect solution. They're great solutions. These eigenstates I'd like to keep in my pocket because they form a complete set. The hydrogenic orbitals, hydrogenic wave functions, form a complete set. I like to keep them. And I like to kind of build this out of those hydrogen orbitals by making linear combinations. That is a mathematical justified approach. Okay? So that is what I'm going to do. I'm going to try to describe the new orbitals of this carbon atom, the orbitals that are a solution of the entire problem, including those extra charges on it. I know it's going to be different from before because it's no longer isolated. But I'm going to describe it in terms of the previous orbitals without those interactions. I'm just going to make a linear combination and arrive at a solution that is very closely mimicking to what I think should be the solution. And this is completely allowed because mathematically I can construct any function out of a complete set of eigenfunctions. I'm going to use that. So, the new orbitals of this carbon atom, which is psi h. The h, of course, stands for hybridized. The word hybridization means a linear combination of unperturbed atomic orbitals. Make a linear combination, you can construct any shape out of them. It is a linear combination, that's what this formula says. You see there, psi n, l, m, those are the hydrogenic wave functions. We've seen them now many times. There's a coefficient in front, which equally depends on n, l, and ml. And then the summation over all possibilities. Right? I don't have to sum over the infinity, I just sum over those orbitals that give me a pretty good solution already. This is an approximation, but it's a very good way of describing my new situation, which is an atom that is no longer isolated. here is example number 1. I'm going to construct the well-known sp hybridized orbitals. What are they? Well, they are, of course, the new function I'm going to call h1 sp equals s plus pz. The s is the unperturbed orbital of the individual carbon. The pz is the pz orbital, atomic individual atom orbital. And I'm going to just make a linear combination, just those two. I can make an infinite series, but I'm going to focus just on those two and see if just taking two will give me a geometry that fits the mold. There's another combination I can make. I can either add or subtract. So effectively what I'm doing, I'm taking those wave function waves, I'm taking an S wave, I'm adding a P wave to it, and I'm going to make two flavors. One adding, constructively interfering them, and the other destructively interfering them, getting a different shape. I can visualize that in the following way. I'm going to take the 2s, which I know has spherical symmetry because of L equals 0, which means no angular dependence. So that's a spherical symmetric orbital. Then the pz, which has L equals 1, has angular dependence. Blue means, let's say, plus sign. Yellow means the negative sign, or the other way around, doesn't matter. Okay, but it means that there's actually a plus and minus sign associated with it. So this, okay, I have to explain that because it's confusing to lots of folks. Remember, this depiction, very specific. It shows the shape of the wave function squared. Okay, wave function squared, the 90% mark. The 90% surface of probability is what is that shape. Okay? So it's because it's squared, it is a positive value everywhere. Yet, here there's two colors which represent plus or minus. Okay, so one side is plus, one side is minus. What does it mean? It means that I'm trying to depict several pieces of information in this, kind of illustration. Okay? The first is the overall shape, the probability of finding the electron somewhere. Remember, the surface is the 90% mark. 10% outside, 90% chance of finding the electron inside, the entire thing. Okay? Not just one side, the entire thing. 90% chance of finding it inside, 10% chance of finding it outside. That's what that surface means. Another piece of information is the color, which is not the wave function squared, because that's always positive. It actually relates to the fact that the actual wave function, so before you square it, can be negative or positive. And that's what that means. That means that one lobe of the wave function is a positive value, the other lobe is a negative value. You square it, both get positive. But I'm going to try to illustrate those two pieces of information. Does that make sense? Remember that, okay? Because that's what these pictures mean. Okay. And the sign actually turns out to be important here because I'm going to combine waves, and waves interfere. So the signs will be relevant. 2s, 2pz, add them up, I get this shape. This is literally what you get. You can do it in a computer, you add those functions up, you get this shape. Looks different. On one side, big bulge. On the other side, tiny bulge. Right? Because on this side, they destructively interfere. On that side, they constructively interfere. Blue constructively interferes with blue, but yellow destructively interferes with blue. Therefore, on this side, you get, smaller amplitude. The other one is the same, but flipped. Right? So I get here two new orbitals that I described with this general method of making linear combinations of the unperturbed, isolated C atom orbitals. And I'm constructing these two new orbitals. I take two atomic, I generate two hybridized orbitals. Remember that. Two in, two out. You don't generate new stuff. Two things, two states, you start with two states, you are still having two states, but they now have different geometrical qualities. This is justified, these shapes, and this is a better description than these individuals in the case the carbon atom is surrounded by other charges. This is way better than that. Okay? But this is situation specific. Carbon can be in different hybridization states because it can be in different environments. That's why I have all kinds of possibilities. Okay, so if I take those two sp orbitals, I can draw them together. This is one, this is another one. I can put those same electrons, okay, in here now, one in each, and you can see that this is actually a very nice arrangement. I have now a kind of configuration, a probability where the electron can be that is now kind of linear. This is of course a linear bonding arrangement of carbon, okay? So you'll see clear examples of that. The justification for this, again, understand this, that this is relevant in situations where carbon is surrounded in a particular way, in linear arrangement of carbon, a linear bonding pattern. This is a way better description than those original atomic orbitals. This is now a better one. It's not perfect, but it's good, and it's easy. I just take the unperturbed orbitals, add them up in different ways, and I get this pretty close, pretty darn close to the truth. I don't have to solve the entire mathematical problem of the Hamiltonian with all the new ingredients in it, okay? That's what justifies the use of hybridized orbitals. It's not a perfect thing. It doesn't fall out of the blue sky. It is an attempt to find a relatively simple description of atoms that are surrounded by other atoms. Okay, I can make more combinations, like I said, depending on the environment of the carbon atom. This could also be a good way to describe the bonding pattern, which is sp2 hybridized orbitals. There are 3 of them. It's the s plus py with the prefactor, then the s plus px and py with different prefactors, and then finally the 2s with the 2px, 2py with prefactors and different signs, as you can see, compared to the previous one. These are 3 hybridized orbitals. I'm using 3 orbitals here, 1s and 2 p's, so a total of 3 atomic orbitals, unperturbed orbitals go in, 3 come out. I don't generate anything new, I just reorder things to fit the bonding pattern better. And these are the things that I get. Why are the prefactors the way they are? Because they are forming a set of hybridized orbitals that are, first of all, individually normalized, and they are orthogonal to one another. Okay? Very important. Because I want these hybridized orbitals to have that property. It's very important to have them be orthogonal, because if they are not, then some information in one is also described by the other one. We don't want that. These states are mutually orthogonal. They are completely independent states. If they are not completely independent, that means that an electron can flow from one to another. That doesn't happen. If an electron sits in one state, it stays there. It doesn't automatically flow to another state, another orbital. If it sits in an orbital, it stays in the orbital. And for that to happen, the states must be orthogonal. You can verify for yourself that any combination, any overlap integral of these will give you 0, and any overlap integral with the function itself will give you 1. Here they are, the 2s. I'm going to combine them, or there are 2s, with 2 of the p's. I take px, py. You can make any combination. You can also take px and pz. It doesn't matter, but you have to take 2 of them. As long as they are all orthogonal, and they are, I can make this combination. I get this. I get 3 out. They have this kind of pattern. Basically, again, looks very similar to the SPs, but now they're organized in a different way. I get a little stump here, so the yellow little knob is low probability. The high probability is on the other side. So I get basically a 120-degree arrangement where there's lots of electron probability. This is the typical sp2 bonding pattern. This one we love. Chemists love sp3, okay? If you don't like this, you may not be a real chemist, I hate to say. sp3 is great. We love carbon. Carbon is, of course, very important for organic chemistry. and sp3 carbon is a predominant bonding pattern. We have to understand the sp3. It is just as before. It's a linear combination of original unperturbed atomic orbitals. I'm going to use all p's and the s all together, and I make the following combinations. This is the first one, second one, third, and fourth. All of them depend on those 4 atomic orbitals, but in different ways added. Okay? You can see the negative signs are in different places. That's the only difference. Again, there's nothing magical about this other than my attempt to describe a situation where the bonding pattern is tetrahedral. This will give me that. And therefore, this is a much better description than the original atomic orbitals that didn't give me that. And I can justify that by understanding that in a different environment, the orbitals will look different. They must. I don't want to solve the Hamiltonian. I'm going to make a linear combination, which is a valid strategy in quantum mechanics, and I'm going to get these, which is a pretty good description of the actual situation. Okay? Because I get this arrangement, the same kind of idea, the yellow, low electron probability, the blue, high probability here, pointing now in different directions, in 4 directions, 4 in, 4 out, 4 atomic in, we got 4 hybridized orbitals out. This is exactly the bonding pattern that I would like to see in sp3. This is a justified way of describing it, because in, of course, really organic structures, the perturbations on the individual carbon atom is such that the orbitals arrange themselves in something like that. All right, now, why stop there? Because I can make linear combinations of all the orbitals if I want, okay? Mathematically, totally fine. I can construct any function out of the complete set. And so I can also do this. If I go to elements in the 3rd row, n equals 3, I can, for instance, do this. I can make a hybridized set out of the 3s, all the 3 p's, and I'm going to just pour in also some d character, all right, to basically create what we call sp3d hybridized orbitals. Or I can throw in another d orbital to create this arrangement, sp3d2, which is, of course, a very important arrangement for atoms like sulfur and phosphorus, which are in n equals 3, and have d orbitals close by in energy. So these are very valid descriptions for understanding these bonding patterns. So, again, next time you look at these hybridized orbitals, try to force yourself to explain why they are the way they are and where they come from. Don't just take them from because it's in a textbook, it must be true. Justify for yourself why coming to these descriptions is a valid way of understanding the bonding patterns of the carbon atom in different situations. Okay, now, and we'll get to this a little bit more in detail, but before I move on, I'd like to show, of course, the different ways in which these hybridized orbitals can help us understand complete bonding between different atoms, right? So if I have 2 carbons together, for instance, they can bind in a variety of ways, depending on their hybridization state. In the case of sp hybridization, which is just 2 lobes, okay, I get this linear arrangement. It means the highest electron density is just simply on axis. That's called the sigma bond. I think we know that, okay? So, the first example, you see 2 carbon atoms coming together, forming a sigma bond in between them, and also forming a sigma bond with, let's say, a hydrogen atom on the other end. Okay? This would be C2H2. If you have C2H2, then you also have, of course, an opportunity to bind or just form a bond with the p orbitals. Those p orbitals, the remaining p orbitals are not hybridized. They are just still have atomic character. Okay, only the s and one of the p's were hybridized. The other ones were unaffected. So they still had the same old arrangement. And you can see that they can make these off-axis bonds. We'll get into it in a moment, where the bonds come from. And then I can make these pi bonds. Pi bonds we will spend several lectures on. So make sure we really understand what those things are. Okay? So what I have then in C2H2, I have one on-axis bond, one sigma bond. I have two pi bonds. So this is like, you know, a triple bond carbon. C2H2. It's an alkyne. This is an alkene where I have, again, a sigma bond. This is now sp2 hybridized. In plane, I have the sp2 hybridization. There's like three possibilities. One is between the carbons, and then the hydrogens can go to the other lobes that stick out at 120 degrees. In the same plane, same on the other side. An on-axis bond, sigma bond, and then this orbital here, the p and this p, is an unhybridized atomic orbital. Has still the same character of the original atomic orbital of the carbon when it was freely floating in space with nothing else around it. And those two unaffected p orbitals can, of course, also form a bond. That's the single pi bond in this alkene. C2H4. Okay, now, what we should do next, because we talk about a carbon atom that is like, you know, affected by something else around it, okay, because there's more charges and so forth, which is true, but that's a very atomic-centric view of what the molecule is. It just looks only at one atom and say, hey, what are the orbitals of that particular atom? That's what this hybridization picture gives us. It doesn't explain anything about the nature of the actual bond, the actual bonds that it forms. Okay? So the hybridization picture doesn't tell us anything about why there is a bond in the first place. Okay? So that is what we have to do next. Okay, so we're going to focus on covalent bonds and ask ourselves, what is it and why is it there? And we're going to proceed with a very similar strategy. Okay? This is how it works. I'm taking two atoms. I'm going to consider a bond between two atoms. I call one atom A, second one I call B. These two atoms, when they're freely floating in space, they have their own atomic orbitals. And we know what they look like. If I bring them together closer, the problem is different now, because if I bring them closer, their charges start to interact. The Hamiltonian is now different. I have to solve a new problem. As opposed to the individual ones, the unaffected ones, I'm going to bring them closer, it will be a different problem. But I'm going to do the same thing as I did before. Okay? In two steps. First, when I bring them closer, and I suspect a certain bonding pattern, first I'm going to consider the atomic orbitals will be different, and therefore I'm going to use the hybridized orbitals. That's one. Second, I have these hybridized orbitals, I'm going to bring them close together and see what happens, where they meet. Okay? This is, of course, just a conceptual story, because in reality, there's no one and two. There's no two steps. This happens all at once, right? It's just a new problem that we can't solve. So that's why we do two things. First, bring them closer. Orbitals, individual orbitals will start to reorganize. Hybridization is a better way to describe these individual points, the individual atoms now. We'll do that. But then we have to understand why when they start overlapping, what is happening there. So, in order to describe that, I'm going to take simply psi A, which is one of the orbitals from the first atom, atom A. And from atom B, I'm also going to take one of its orbitals, I'm going to smoosh them together. I'm going to say, well, the new situation is basically this and this together, combined in some sort of way. I'm going to make a linear combination of orbitals that come from different atoms. This is different from what I did before. The basic idea is the same. I'm going to again make a linear combination of several things. But in the previous case, it was an atomic centric thing. I had one atom and I made just combinations of its orbitals. Now I have two atoms. I'm going to make a linear combination of their orbitals. That's why it says A and B. It doesn't come from the same. A and B are from different particles. Now I'm going to make a linear combination of those different particle orbitals. And the first attempt is very simple. I'm just going to say one plus the other, or one minus the other. Okay? What does that mean? Well, remember, those orbitals, even though we visualize them as lobes, because it's easy, it's probability, we understand that. But the actual thing is actually a wave function, which has a sign. Right? And I can make combination in two ways. I can have either the plus sign or the negative side of the orbital interact with the other one, which is what waves do. Waves interfere. This is two possible interference patterns that I'm generating between two waves. Wave 1 comes from particle 1, atom 1. Wave 2 comes from atom 2. Together, they will interfere and create a pattern which will now be my new orbital that describes the whereabouts of the electrons, where the electrons can be. It's wave interference. Okay? So, let's look at these properties for a second. Because what I want this new combined orbital, which is now my bonding orbital, the orbital that actually describes the bonding between the two atoms, to have the same properties that wave functions have in general. I want them to be normalized. Okay? So, when I take the plus combination, that's the psi plus, times itself, the psi plus, okay, this is no longer an atomic orbital, this is now a molecular orbital. The molecular orbital times itself, I want it to be 1, because that simply means it's normalized. Okay, so we can do that. All right, I just take the shape of the wave function, psi 1 plus psi b, square it, and then integrate it over space. That's why dv is. Okay, and try to solve it. It turns out, okay, you see here n squared because I squared it. I get, of course, the individual terms squared. That's the first. The second, one for A, one for B, and then the combination term. Always, when you square something, you always get square root of one, square root of the other one, plus the combination term. The square of A and the square of B is just the normalization condition for either one of them, which is 1, because the atomic orbitals were normalized. So it's 1 plus 1, plus whatever this is basically the overlap integral. Psi 1 times psi b, integrate over space, is basically the overlap integral of the two individuals. Okay? And I'm going to call that s. So what I have then is n squared equals 1 plus 1 plus 2s, which is this. And that should be 1, and therefore n equals 1 over 2s2, and then between parentheses 1 plus s square root. This is the normalization constant that goes in front of the wave function. So now I have a normalized molecular orbital. A normalized molecular orbital, which of course depends on what s is, which we haven't really said much about. Okay? And that's the form. I also want, let's say, these two molecular orbitals that I can form, one with the plus combination, one with the negative combination. One is the constructive interference, the other one is the destructive interference. Two waves interfering can be happening in two ways, constructive, destructive. Those two guys, those two are valid solutions. Okay? I want these valid solutions to be orthogonal to one another. That means they have nothing to do, they're completely independent descriptors. And therefore, this should be true, that this guy and the other guy, the plus combination and the negative combination, integrated over space should be 0. I want it to be true. So I'm checking that, and that is actually the case. Okay, so here's the plus combination, this is the negative combination. I'm going to multiply the two and see what I get. This is what I get. This cross term is not there anymore, because you can see very easily, because there's a negative sign here and a plus sign there, that the cross terms cancel out. I only get that and this, and fortunately for me, that is just the normalization condition for each of the individual atomic orbitals. 1 and 1, 1 minus 1 typically gives you 0. Okay? And in this case as well. So, good. I have here now 2 molecular orbitals. Very important to call it molecular, because this is no longer an atomic orbital. This is the joint probability of where the electrons can be, because 2 atoms are interfering with one another. The orbitals, the wave functions from 2 atoms are interfering, forming a new probability distribution, which we call the molecular orbital. I have 2 versions, 2 interference patterns. Let's make that a little bit more explicit by drawing what these things look like. You want to draw the orbital, you're squaring it and plotting it. The first one is the plus combination. You square it, okay? You see here, it is basically the first one and the second one, probability distributions. And then, of course, this overlap thing, overlap between the 2 orbitals, with 2 in front of it. So, what I'm getting is, I have the original distribution in the orbital of particle A. This one is particle B. Their distributions stay. It's just one plus the other, plus something extra, which is this 2 times the overlap. Okay? That's the constructive one, of course, because I get something extra. This extra term, this green, in this green box, is an extra probability that I'm getting because of the constructive interference. So, it's not just adding one plus the other, and then that's it. No, there's an extra term, which is maximum actually exactly in the middle, because there the overlap is the highest. I get an extra electron probability smack in the middle between those 2 atoms. If those 2 atoms are the same, 2 carbons, it's actually exactly in the middle. I get a higher probability of finding the electron in the middle that was not there before, because if the 2 atoms are far away, it just ceases to exist. When you bring them closer, it's one plus the other, plus the extra term in the middle. Okay? The other one is this one. It's the same. And now, of course, there's a negative sign, and that means instead of getting an extra probability of finding the electrons in between the atoms, I now find a depleted probability. It's less. There's less probability of finding the electron exactly in the middle if you put them closer. This is important, because, of course, that's an anti-bonding orbital. The first one is bonding, the second one is anti-bonding, but we have to understand why. Why we call that bonding and anti-bonding. The reason is this. We want electrons, a high probability of electrons to be in the middle between the 2 atoms, because if you bring 2 nuclei together, they are both positively charged. If you bring them close together, they will repel. But if I build in extra probability of negative charge in the middle, that will be offset. Therefore, energetically, I create a very favorable condition if I put extra electron density in the middle, because it offsets the repulsion, and if you offset repulsion, you get lower energy. So, the bonding orbital is a lower energy situation than the anti-bonding orbital, because in the anti-bonding orbital, I get exactly the opposite. Where I needed the electrons the most to offset this repulsion of the nuclei, I now have less. And if I have less, or actually 0, that means that those nuclei will feel one another, and they tend to drift away. That's anti-bonding. Anti-bonding is literally not bonding. Okay? It's actually a repulsive scenario. If you are in that orbital, if you are an electron in that orbital, you add to the anti-bonding character of the bond. This picture you may have seen before. The psi plus, remember, this psi now is no longer an atomic orbital, it is a molecular orbital, which is constructed by me and you. By adding up 2 orbitals from different atoms. This is a new thing. I did it in the plus way and the negative way. In the plus way, you see the dotted line are the individuals, but there's an extra density exactly in the middle. That extra density of electrons helps me offset repulsion, drags down the energy, more favorable. In the psi minus, I get the exact opposite. You see now, they cancel out exactly in the middle. There's 0 probability of finding electrons there. This is the probability density, as you can see, okay? You see it's 0 here. It's high there in the bonding, it's 0 in the anti-bonding. Where you needed the electrons the most, they aren't there. And therefore, the nuclei feel one another, and they drift away. It's literally an anti-bonding orbital. Okay, so understand where these things come from. Verify it for yourself in your head. Try to ask yourself the question, why is this happening? And also realize that this is truly is a wave behavior. Classically, we are unable to describe this, because in classical mechanics, we don't use the wave concept, and therefore there is no interference. Because waves interfere, we have this. We have a bonding and anti-bonding situation. It's purely a quantum mechanical thing. So, in the case of atoms, we absolutely needed quantum mechanics, but in the case of explaining why there are bonds in the first place, we also need quantum mechanics. Classically, you will not be able to do a good job. Okay, that's all. See you next week.